Trebuchet design. A trebuchet is a machine or a catapult which has a long arm-like structure that throws a projectile across a range of distance. It was first used by the ancient Greeks and Romans in the 12th and 13th century as a combat weapon. A trebuchet works by using the energy of a falling counterweight, which is the gravitational potential energy, to launch a projectile using a mechanical advantage to achieve a high launch speed, which is the translational kinetic energy. These are the requirements by the LFS demolitionists. The full-scale trebuchet must have a pivot height of 1.5 meters. The maximum allowable counterweight is 300 kg. The total mass of the arm must not exceed 25 kg uniformly distributed over the entire length of the trebuchet. No energy sources other than the counterweight are to be used to propel the projectile. The materials required. The trebuchet is mostly made of treated pine wood. The sling pouch is made out of leather. Steel and iron gusset plates is used to strengthen the wooden joints along with steel rods for the fulcrum. The arm is made out of carbon fiber as it has low mass and strong enough to sustain the weight of the projectile. Jute ropes is used to hold the counterweight and will be used to pull it up to the position which prevents the splintering of the wood at key joints. Tar and pitch is used to prevent the trebuchet from weakening. The counterweight is made out of reinforced concrete, which makes it stronger and less brittle.
In order to make our trebuchet more appealing to LFS demolitionists and to the television audience, our team's trebuchet must not only be efficient but must also have an appealing design to the trebuchet. To make our trebuchet more efficient, we have to consider the data collection and testing method of our trebuchet. This is to ensure that we have the right values for the different independent and dependent variables. As you can see from the slides, there are a set of processes that are involved in the collection of data. For the most part, the data is collected using the virtual trebuchet simulator, which can be found on the internet. First and foremost, the fixed, dependent and independent variable are identified. As you can see in the table below, there are 3 independent variables and 2 dependent variables that must be taken into consideration. The values of the independent variable will be modified and the result, which is the dependent variable, will be obtained. The dependent variable is modified and the test will be conducted based on an estimated range. This process is repeated for a number of times until a graph can be plotted involving the dependent and independent variables. From there, a decision will be made to determine the optimal value for the dependent variable so that it can be implemented on the trebuchet. Based on the data collection method that our team has used, we have identified the optimal values to be used for our trebuchet. The values obtained can be seen on the table from the slides. Our team's trebuchet counterweight is assumed to be made up of multiple rectangular slabs stacked on top of each other, which makes the mass of the counterweight changeable. The value of the long arm is chosen to be 1.35 meters as to make sure that the arm is long, but still allows for the movement of the arm. The length of the arm must not be longer than 1.5 meters as the arm will go through the ground if it is. It's common sense. Based on Siano's key fact, the optimal ratio between the length of the long arm and the length of the short arm should have a ratio of 3.75 to 1. The length of the sling should also be around the same length as the short arm. The length of the weight is chosen to be 0.2 meters as the weight cannot be too long or too short. The mass of the arm should be as low as possible as to increase the range of the projectile. The mass of the arm is dependent on the material used. Thus, a mass of 0 kilograms is not possible.
There are 3 main theories governing the motion of the trebuchet. The first one would be the principle of conservation of energy, whereby the larger the mass of the counterweight, the larger the gravitational potential energy, and hence the larger the amount of kinetic energy converted into the projectile. The second one would be the principle of mechanical advantage. Basically, the counterweight, it pivots around a much shorter distance as opposed to the projectile end. Hence, the projectile end can achieve a much higher linear velocity. The third one would be the falling of the counterweight. It produces a torque on the throwing arm, causing it to rotate clockwise. Hence, the projectile experiences acceleration, causing it to move outwards. There are quite a few highlights in our trebuchet design. The first one is a light gate is used to ensure that the projectile is released at a proper angle. And a sensor is also attached to the side so as to ensure that the angle is as per the requirements that he or she would like to achieve with regards to the range. The sling also has a cover which will only be triggered to open once the certain angle that is set by the user is achieved. The base of the trebuchet is heavy and detachable wheels are attached to it. The wheels are basically there to facilitate movement so that the trebuchet can easily be moved from one position to another, and also it can be removed so as to secure it into place once the specific place has been set. There are also linearly spaced holes on the arm. This reduces the mass of the arm, allowing the trebuchet to achieve a much higher range. Furthermore, the movement of the inertia of the counterweight is designed to be small. Hence, we've decided that the shape would be a rectangular shape. But to achieve the highest range, the counterweight has to be the maximum.
Alright, here we have two graphs, and for the first graph, as the mass of the projectile increases, the range actually decreases, and that is because lighter projectiles travel further as less work needs to be done to lift them up against gravity. Therefore, if mass is reduced, then less of the GPE of the counterweight needs to be converted to the GPE of the projectile, and more kinetic energy will be available for the projectile. For graph number 2, as the mass of the counterweight increases, the range increases. And according to the formula PE equals mgh, an increase in mass means an increase in GPE of the counterweight. It is this GPE of the counterweight that is eventually converted to the KE of the projectile. So an increase in the GPE means an increase in the KE of the projectile. Speed increases, therefore range increases. Here are the drawings, and in conclusion, our design of the trebuchet implements modern technology using ancient technology as an inspiration. Understanding the principle of conservation of energy, principle of mechanical advantage and torque, we have modeled our design with the help of the virtual trebuchet simulator. It has an energy and range efficiency of about 0.6 units. Furthermore, it is made mostly out of treated pine wood, a material which has a high resistance against decay and an aesthetic natural design. Our design is also eye-catching as it has a unique pentagonal base. Therefore, it is based on this reasoning above that our design can and should be implemented.